Alright guys, hello everyone. We start our weekly design and computational design tutorial session. Today we're going to be talking about some, let's say, not obvious ways of creating complex geometries with the help of maths, especially trigonometry and other quite useful Grasshopper features such as Grasshopper and mathematical equations and functions. And as a key study project, we will be demonstrating the lattice structure that we developed as a case study project for one of our interiors. So let's move on. Let's start our session. There we go. I remind you that we have our live chat available, so if you have any questions or ideas, please drop a message into the chat so that we will be able to answer it once we finish. And maybe we'll consider it for our next tutorial sessions. So first of all, let's put the bifocals here. So you will be able to see the names of all the components, and the image that we are going to be working on is in the initial part of the stream, so you can see it. But to put it short, we're going to make some wavy surface shown by a lattice structure, which is kind of useful as a lightweight fancy looking structure. But of course the main benefits of this structure can be not only its aesthetics but also its structural performance, economy of the material, and some other features which we will be discussing a bit later. So let's move on. Let's start from creating our wavy surface. I think the simplest way, again, I don't want to draw anything in Rhino. I want to start from the software directly. So let's construct a point. Right, I'm gonna zoom to see it. I'm gonna switch on the grid. Yeah. So we see our construction plane, which is like C plane. On Windows, if you press F7, it's a hotkey to disable the grid. So I'm gonna just switch it off. I'm gonna draw the line SDL to start our surface. So let's draw it along the x-axis. Let's make it pretty long. I'm gonna go for 900, let's say, millimeters or something, or any other units actually, doesn't matter. Yeah, so if you of course if you have in mind some specific interior or some specific facade or like some dimensions, it's better to consider the units. But right now we're just gonna make it we're just going to use the units which are convenient for us, basically not too big, not too small, something where we have enough flexibility to move and also not go with too many decimals behind. So yeah, because unit, if you're not working with, if you're working with some abstract project, it makes sense to work with values that are convenient for you to move the slider and to yeah, which are convenient for you. If you're working with some actual units, of course, it's a bit different story. So here we're gonna make it, we're gonna make our life a bit easier. After that, I'm going to extrude the curve to make surface. Let's go along the vector and let's make it actually a factor of this value. Let's say it's going to be 40% or 45% maybe, or maybe actually a bit more. No, actually it's fine, doesn't matter. We will be able to figure it out a bit later once we have our surface. So this looks good to me. We can play with the ratio of the design, and when we change the dimension, you see it gets proportionally decreased or increased. So yeah, 900, fine, 0.7. Maybe I'm gonna go a bit lower, let's say 60, yeah, something like that. Alright, so then I'm gonna divide my surface into more or less squarish grid. So let's go for something like, yeah, if we want to make a squarish grid of points, it's important to make sure that our height and our width are going to be the same number, right? Or more or less the same, because sometimes it's not possible to divide the surface into perfect squares. But at least let's try to make it as squarish as possible, because it's gonna help us with our function and with with the aesthetics of the shape and with manipulating its shape. So let's use the dimensions component, which if someone doesn't know, it comes from, if you press Ctrl Alt and left click on the component, it will show you where it comes from. So it can be found in surface, analysis, dimensions. And now we're gonna take the division component, so that we'll be able to actually take the dimensions of our cube, our square. Let's say I'm gonna start with 30 for now. So let's take it like this, and let's light it. Okay, whatever. And let's make a divide surface. Let's use the divide surface component, which will help us to get the grid. Okay, looks good to me. Maybe I'm gonna go a bit lower. In fact, I just want to make sure that it never reaches 0, so I'm gonna edit it to make the lower limit not too small, because in some cases, if you if you are too brave and you move the slider too much to the left, you can achieve a very low value, so that your surface will be divided into too many points, and this might result in your computer crashing. It probably will not do any harm to your laptop or your PC, but it might mess up your process. So it's always better to not risk this. I'm also going to save the document in case if something goes wrong, so I'm going to save it with today's date and in a special folder. Let's say call it relative demonstration, and there we go. I'm going to decrease this to 15 so that the grid becomes a bit denser, right? And now basically we need to take those parameters to actually we have the normals already, so it should be fine, I guess. And now it's time for us to start moving this, moving those points and making this kind of wavy surface. In case if you, like me, do not have a degree in maths and probably studied maths on the school, it can be quite confusing to use these trigonometrical functions. Although I know that most architects and engineers, they have like higher maths and some other technical subjects in universities. And probably if you are working with Grasshopper, you already have some understanding of these tools. Still, sometimes for people who are not like mathematicians, let's say, it can be quite confusing how all these functions work. So I'm gonna show you some tricks, and as for us as designers, we're quite visual people, so let's say we're not gonna use only functions, we're gonna use the graph mapper to take a part of our part of our mathematical job from us. But we're also going to use some functions, like sine functions and other tools. So right now, we are dealing with a tree, and basically what I want to make sure that each of these rows of points will go as a separate wave, like as an individual wave. So they will form a wave altogether, but each of them will be slightly different. This is how we're going to get a wave not only along it, but also across the surface, right? So to make sure that each of these rows is a separate branch, let's check how does the tree structure look like. So I'm going to use the tree statistics component, which is the best friend of any person using Grasshopper. And I'm going to use the tree branch component as well I'm going to use it to pick the branch that I want. Take the list item and connect it to paths, and there we go. All right, you see, basically this is our branch, which means that basically we can use those yeah, we can use this data structure. This is fine. So okay, let's now take the tree statistics once again from here, and let's use it to generate let's take the tree count to make sure that we generate a number for each of the tree branches. Yeah, so we take the range. Let's not forget to right click and go to expression and set x minus 1, because range normally generates one more values than we supply. So if we supply 37, normally we generate 38 values, but we need to have precisely 37 values. So we need to, let's say, artificially subtract 1 from the value that we supply. So let's connect it to the graph mapper, and let's go to graph types. Let's take sine graph. I'm gonna set it somewhere here, let's say. And yeah, then I'm gonna take the bounds, the remap numbers. This is like a standard setup for the graph mapper. And I'm gonna construct the domain from let's say 1.2 to 0, something like this. Yeah. Okay, right now we have our setup, like very basic one. You see that every number is slightly different from here. Yeah, so we can take the move component. We have the points here, right? So we can connect them here, and we're going to use the amplitude component. We get the normals, which is like the vector, and then we get the amplitude, which is the value generated from this component. It's important to graft this output, right? So it's graft and connect it here, because we have one value per tree branch right here, but they go as a list, so they are not grafted. They all are in the same sequence basically, right? So it's important for us to make sure that each value will go for the corresponding branch. All right, so now we have it, and let's connect it to move, and let's see how will it look like. I'm going to hide everything which was before, and I'm going to look at yeah, you see that each line gets moved a bit differently, right? Also, as the value here is very low, see, it's not very visible, right? But if we increase it further, like to 100 at least, you see we start getting this wave. Yeah, it's fine as a very basic shape. It's okay. We can play with this graph to make it a bit different. But what I don't like is that it changes only in one direction, right? So with this graph, we basically deform the shape only in a vertical direction. It doesn't change along the form, right? So this is not exactly what we want, and now we will try to make it a bit more interesting. So first of all, let's add this graph effect here as well. And I'm not gonna just I'm gonna use the sine function for that. So I'm gonna use the very simple expression, right? So I'm gonna keep the first input as x, and the second input I'm gonna change for a, which counts for amplitude, right? And here I'm gonna type equals sorry, no, yeah, talking about people who don't know maths very well, I'm the clearest example. Yeah, sine from x. Yeah, this is the expression that we're gonna use. Okay, so let's say I'm gonna supply something for a. I'm gonna supply something for x. You see, sometimes expression behaves a bit. Expression component behaves a bit weirdly, so it's important to check. Works. Okay, yeah, here I'm gonna go back to 1.2 maybe, something like this, yeah, and then I'm gonna connect it to expression, and here actually I want to go a bit more extreme, maybe even more. Maybe we can make a slider from, let's say, from 0 to I want it to stay at 120, and then I want the upper limit to be 150. So this is another small trick to create sliders with a given bounds. Right, you type in the first number, which is the lower limit of the slider, the next one, which is, let's say, the current value of the slider, and the last one, which is the upper limit of the slider. So yeah, let's connect it to the component, and let's actually connect this to here. Yeah, you see that didn't change anything, right? Okay, so let's now graph it here. So here, and let's see. Oh, sorry. Yeah, of course. Because actually we need to 1 second. Thankfully, I have this script. I have already done it before, so I have it saved. Yeah, we need to. Okay, fair enough. Right, this one is. Yeah. Perfect. Yeah, okay, fine. Yeah, let's go for it. Okay, so here, as you can see, we need to graphed our values, because for each branch we need to have our own set of values. But then not only we need to have our own value per line, per row, basically per row of points. We also need to make sure that it will change inside this very row, right? So that one value will be different from another. And for that, we need to construct a domain first of all, right? We're gonna set it to, let's say, we're gonna use a range. Again, we're gonna say x-1. We're gonna connect the length of each list right now. Yeah, we're gonna connect it here, so that for each point, right? For each point, we will have its own value now, right? And here, for each of those branches, we will have its own domain, right? And then we will have it like that. Yeah. So actually, we don't need to graph it here. Okay. So now we need to provide a domain. Let's start from a super simple domain from 0 to, let's say, 100, something like this. I take this high value just because I want to make sure it's yeah, I just want to make sure it's gonna be working. And actually, yeah, if we connect it like this, you see it just moves like that, right? Because the first point in a row, it doesn't get moved. Well, the last one gets moved by 100. Yeah, and it's gradual, because range gives us a gradual increase of the values. Okay, so now we will make sure that we have a separate domain for each row of points. Yeah, so let's take this domain. Let's connect, instead of 100, let's connect this number. Yeah, and let's connect it here. Yeah, because it's a really low value. Let's connect 120 here. Yeah, you see, we start getting this kind of wavy thing here. Yeah. So okay, and then if we change it, we start getting these waves, and from this side it's gonna be straight. Yeah. So now we already have a slightly more interesting shape vertically, like across our surface, but along it's still very linear, right? So now we need to add some components to make it move along the surface. Yeah. Okay, so for that, we're going to take, we're actually going to connect this thing here, and we're going to take the sign of each of those values. like this. Yeah, we don't need to multiply it because we already multiplied by 120 here. So let's connect here. You see, right? Basically, same thing. Yeah, very similar. Okay, so now let's finally do something that will make it look more like a wave rather than just this kind of ruled surface, which it is right now. Okay, so let's make the domain a bit more interesting. Let's use the pi. So we're gonna multiply the values by pi, and we're gonna make it negative. So we can go from minus something, right? And then we're gonna add another value. I'm gonna make something like 12, and we're gonna subtract those numbers from here. We can actually start a bit lower. Well, and let's use those values as our domain. See? Okay. And maybe I'm gonna make it a bit less saturated. And yeah, here we can start moving. And as you can see, we start getting our wave. Yeah. So 1 second. Sorry guys, it's evening here, so I'm a bit a bit confused. What minus this values here? Oh, it seems like everything works. Should be fine, but yeah, sorry, my bad. Should be the opposite. Yeah, there we go. Okay, so yeah, as you can see, we get this this wavy texture, and now I'm gonna explain a little bit about how does it work, how each of these components work in individually, right? So we can decrease this amplitude a bit, let's say to 60, something like this. You see that basically here we get the shape which the graph mapper shows us the let's say vertical distribution of values, right? Like the vertical deformation. This component, this number, refers to the let's say length of each of the waves. Yeah, so now it's very long, very like dramatic shape, let's say. Now it gets much calmer. Yeah, so okay, fine. This number works for the number of waves. Yeah, so it tells us how many waves we're gonna have. Yeah, so for example, we can have a lot of waves and still we can have them pretty long. Yeah, so you see that we get a really exaggerated texture. So okay, right now I'm gonna keep the values at something like this. Yeah, and now we can also, yeah, basically that's pretty much it. Okay, so looks good to me. Let's move on. I'm actually gonna keep this script on the screen for a second. So for those of you who are repeating after me, you can or who will be watching this stream, this live session later, you can pause the video and check the components. It also has all the names here, thanks to Bifocals plugin, which use. Yeah, sorry, a second. Let's move it down, and there we go. Okay, let's count to 5 and let's continue. 1, 2, 3, 4, 5. Perfect. I assume that everyone has had time to repeat this. I minimize the screen and I move on. Yeah, also I'm gonna change this parameter a little bit to make the weight a bit longer. Yeah, that's it. Okay, perfect. So as you can see, we are not using only the graphs to make our complex shape, but we're using some mathematical functions to control the length of the wave, to control the amplitude of the wave, yeah, and to control the number of those waves, yeah. So like it's pretty much control. We can pretty much define all the things here. Okay, so now we need to actually start making a surface for our lattice, because the lattice is going to be built between two surfaces, and we're going to use a pufferfish plugin. By the way, we're going to attach the list of all the plugins to this and the links to download them to this live stream. So yeah, in case you want to repeat and to have them in your Grasshopper folder, please don't hesitate to download them. We probably might need just the pufferfish plugin and the Weaverbird, of course. Weaverbird is another really useful mesh tool for Grasshopper. Actually, Weaverbird we don't necessarily need it, but it's better if you have it in any case. So. Okay, so let's start making our surface. We can either just go from like surface from points, something like this, yeah. And we just need to flatten this structure. We need to, sorry, actually I'm gonna flatten it here. I'll explain why in a few seconds. And here for the U count, we need to provide this number, which we supplied here. But we need to right click, go to expression and say x plus 1. There we go. See? We get a surface. Another way to make a similar thing can be this. We can use the interpolate and we can flatten the curves and we can make a loft for them. This is another method which is almost the same, but it takes more time to compute, so I would suggest us to use the surface from points component. Great, yeah, and as you can see, we can change the surface. That it will change with the points. Well, this is pretty obvious, I think. So, okay, let's move on and let's take another surface. Actually, yeah, actually, I just want to make another surface. So I'm going to take this extruded geometry and I'm going to move it by, let's say we take this surface, we make a relay, so our script is a bit more ordered. We're going to move it, this part. And I'm going to move it by 60 times, let's say 1.20, let's say, something like this. So my idea is to move this surface to the front a bit along y-axis, yeah, a bit more than it was in the beginning, so that these two surfaces do not collide, yeah, or do not intersect, so to speak, yeah. So I'm going to hide this thing, and yeah, we're basically left with these two surfaces. All right. So now I'm going to take the yeah, actually I'm going to take the pufferfish plugin and go to twisted box tab, and I'm gonna use the twisted box to surfaces component, which sounds ideal for our goal. As you can see, we make twisted boxes between two of our surfaces. And now, as you can see, we have a problem here, right? This problem is not really obvious and not really It's not really too complicated, I would say, but and for now it's fine. But you see that these boxes, they are not orthogonal, right? They don't. We have these. They're not horizontal, so to speak, right? The bases of these surfaces. So sometimes I would actually recommend you guys to use another approach without surfaces, right? Without any surfaces, using just the curves. So we're going to interpolate those points, and we're going to interpolate those points, right? The points from the undeformed surface, like from divide surface, from the very initial one. Actually, sorry, my bad. We need to, yeah, no, actually, all good. We just need to move those points by the same vector as we did it here. So just to make sure that they will not, these curves will not, yeah, they will not intersect with our first surface. Yeah, so we're gonna take them here. This, we have them here, right? Actually, I might. Yeah, those are too many curves. So I'll explain what we're gonna do. We're gonna make twisted boxes between those curves. But right now there are too many of them. So maybe, just for the sake of computational power, and also to not make everything too complicated and too heavy, we can, instead of taking the points, we can take the surface and we can just divide it into points again. So let's take the divide surface, dimensions, this surface as well. Actually, we will use the same. It's also very important to use the same numbers, the same results from U and from V for both surfaces, because if we take the dimensions for each of those surfaces, their dimensions are clearly different, right? So it's not going to help us, but it's going to, on the contrary, it's going to create a lot of problems, because we will have a mismatch of the data, right? So let's just take it like this. Yeah, right now we have all the surfaces match. Sorry, all the points matching. There we go. Yeah. If we look at them from the front, you see we still get kind of. Ah, no, actually. Yeah, actually we need to rebuild the surface first. And let's see if it helps. Not really, actually. The curves are. Yeah, there are two ways to fix that thing. Actually, one of them is to one of them will be to take the level of the curve. We can use the evaluate curve from here. Yeah. I'm going to evaluate the straight curves from the straight surface. Yeah. And I'm gonna take the center point of them all, like this, yeah. And I'm gonna make a plane, like an XY plane, to intersect it with the other surface that we have just created from this one, yeah, like the wavy one. Just gonna say brep plane. There is a component to intersect them. It's a default Grasshopper component, so it's really really easy to find it. It's here in intersect. It's physical. No, sorry, mathematical. Yeah. Brep plane. This one. Okay, so let's take those planes. Let's intersect it, and yeah, takes a bit of time, but as you can see, as a result, we get the curves which are perfectly aligned. Yeah, so they are all planar and they all are, yeah, actually they're good to go. And they all form, actually they all form pairs with our within our framework. Yeah. An important thing is actually they even have the same data structure. But for us right now, it's important to trim tree and to make sure that we have lists instead of trees, right? So I'm gonna simplify it. Okay, I'm gonna use shift paths instead. Yeah, that's the reason why I prefer to use shift paths instead of trim tree, because shift paths works fine even if the result it flattens the tree. So you can see it worked. Yeah, let's move on. Let's take it here. Let's put it here. Here. Yeah. So okay, now we have two lists of curves. And now, again, we go to pufferfish, we go to twisted box, and now we need to select the component that is called twisted box. I'm not sure if it's tube or no, sorry, it's not tube, it is twisted box sweep variable. Sweep. Yeah, it's this one. Twisted box sweep. So how does it work? Let me make another awful sketch for you guys to make it a bit easier to understand. Basically, it takes 1, 2, 3, 4 curves, and it starts making twisted boxes between them. So as you can see, this is R1, this is R2, R3, and R4. See, right? So it goes tuck, 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 and it does the same thing here. Yeah, so basically it starts forming twisted boxes and so on and so forth. Yeah, so basically it starts forming twisted boxes through these sweeps, and the shape of those sweeps can be any. It doesn't need to be straight, right? So it can be yeah, even our sweeps are good to go for that goal. But it's important to select those sets correctly. Yeah, like R1, R2, R3, R4. Yeah, so let's actually make those lists. So here I'm gonna shift list. Actually, let's actually make let's numerate our curves. Yeah, with the point list component. I'm gonna make it. I'm gonna make the numbers big. Yeah, so they're visible. See, 0, 1, 2, 3, and so on. And we'll do the same thing here. Yeah, but we won't do it to understand the concept. So yeah, and we need to shift list to create sets of curves. Yeah, so and we need to make sure that it's inverted so that this curve doesn't go anywhere. So let's say that for the first curve we're gonna set for R1 we're gonna select this set. For R2 we're actually gonna do quite the opposite. We're gonna shift it not up but down. Right, so we're gonna right click here, go to expression and say x minus 1. This is sorry, my bad, minus x, because it should go down. Yeah, so this curve doesn't play, only this does. Yeah, then here for this set we're gonna take another one with a positive shift, sorry, with a negative shift will go first. Yeah, like those ones. This curve will be the one that we need, and then this curve will be the last one that we will be using. Yeah, so we have 4 sets of curves here, and we connect them all like this. Yeah, another really important thing is that we need to make sure that these curves are flipped correctly. So what we're gonna do first of all, before we actually shift the paths, we're gonna say flip curve, and we're gonna use those curves, like the straight ones, as the guides for those ones, for the intersections. Yeah, so this, there we go. Yeah, you see that now the curves go in the same direction and they are straight. I mean, we can. You see that we also don't have these boxes always perpendicular, right? Actually, like how it looks from the top. We don't have them always perpendicular, right? But we can solve it the same way as we did for with the intersection. We can also divide the straight curves first. We can make y-z planes and intersect it with these curves to make those divisions. But I'm not gonna do it right now. If any of you has a suggestion how to make it, you can you can leave it in comments, or if anyone would like to see how it can be done, yeah, just drop a comment, and I will maybe talk about it in one of our next sessions. Let's see. But yeah, in any case, our today's goal is to understand how to populate this geometry with lattice making modules. So that's what we're gonna do now. Let's go to twisted box sweep. Let's also fill the parameters. Yeah. Actually, do we need to do it? Okay. Shall we define by how many values should we divide it? Let's take the range and let's connect something like, I don't know, 24 maybe, and let's connect it to T. You see that the grid became denser, so yeah, currently we can just control the number of twisted boxes that we have. I like the number 19, so I'm gonna keep it like that. And yeah, let's this is basically our grid, so we are ready to populate it with our lattices, with our like lattice modules. How are we gonna do it with the modules? Yeah, we're gonna start making these modules on the ground. So I'm gonna make a really simple one, really simple exercise. I'm gonna take the starting point, and I'm gonna move it a bit forward, so we will have it in front of us. This point, let's move it by along y-axis. I'm gonna move it by, let's say 400, maybe 200. Should be fine. With minus x expression. Yeah, sounds good. Looks good to me. Let's take a center box component. Let's actually bring this entire thing forward. Let's take it here and let's bring it to the end of our code, because it's just going to be visually more convenient for us to have it here. And for the dimensions, I'm going to set something not too extreme, but something which is visible for me. So I'm going to put it 100. Oh, it's too much actually. Don't forget the center box, it takes 100 up, 100 down, 100 to the left, 100 to the right. So if you want the box to have dimensions of 100 by 100 by 100, you need to set up the dimensions half as big as you want it to be. Maybe another nice option to control the dimensions of the box can be connecting the division component before, right? So something like that. There we go. Now the dimensions of our, if we set it to 100, means that the dimensions of our box are 100 by 100 by 100, which is exactly what we want, right? So this is like another small trick. Okay, so now I'm gonna take, I'm gonna scale this box a bit down. Scale this to, I don't know, something like, and I'm gonna use the center of this box as a scaling point. We can also use this point, but we don't need to create a separate center component. We can make it smaller, let's say this amount. Yeah, and now I'm gonna take the brep wireframe, or actually, do I need it? No, we can just say deconstruct brep here, here. Yeah, I'm gonna use the line component because this box is the very same box as this one. It's just scaled down, which means that the order of all the vertices and like their position is going to be the same, just smaller, which means that we can take the line and connect all the vertices with each other like that. Yeah. Okay, so we get these lines, and then we need to take the edges from the smaller box. Yeah, like from this one. And as you can see, we get our geometry almost ready to be placed into those containers. Yeah, so if we merge it, and then yeah, so flat, then we say box morph. Again, it's another default component from Grasshopper, so there is no need to yeah, no need to install any plugins for that. We're going to use our initial box as a reference box, and those twisted boxes as our target boxes. And also be careful, because here you see that it basically took and copied one curve to every box. But we need to make sure that this entire entire list of curves gets placed into every single twisted box. For that, we need to right-click and graft the twisted boxes. So now we get our lattice complete. Yeah. Okay, but you might ask, how is this exercise different from the hundreds of exercises related to twisted box that we can find on YouTube? And you'll be right. That's why I'm gonna spice it up a bit and show you one more useful trick, which can be used not only for lattices, but it can be used for almost anything in Grasshopper, like for any task. And yeah, basically enough talking about it. I'm just gonna show it to you. So let's go to front, and let's switch off the grid because it's quite annoying, and let's draw a curve for as an attractor. Yeah, I'm gonna draw this curve. I'm gonna go to perspective, move its points a little bit. Like again, also different from all other tutorials. It's not. But now I'm going to show you something which I personally find quite useful and quite interesting. So let's imagine that we are making a parametric wall, which is going to be 3D printed. That's why we don't care about making every single cell the same. We can make each of them unique, right? Because we're going to print them, or we're going to manufacture them in some other way. But again, we don't care about standardization. We can make them all different from one another, but we want to make sure that our wall will be I don't know, let's imagine that each of these boxes has a solar panel inside, and we want to orient them in the best way possible to absorb as much sunlight as possible. So we need to make sure that each of those boxes will be rotated differently. How can we do this? Well, we can rotate the central box, of course, but right now all these elements are unique. They are deformed, right? So there can be two methods actually to address this. One method, I'm actually going to show you both. Let's start from a simple one. Let's say we want to have the same box in each of those geometries, and we want it to be rotated. So how are we going to do it? Well, let's take it this way. Let's instead of taking the lines and placing them into those boxes, let's take the points instead. Yeah. So instead of taking the lines, we can take the points. Yeah. From here. And we're going to place them in. Okay, sorry. Actually, no. Actually, let's. Sorry, my bad. Let's go with the lines first, and then I'm going to show you the method with the points, because I think the lines are a bit. We're already there, so it's going to be a bit easier to go from here onwards. So let's take the lines, and let's say that, as we discussed, we need to rotate each of those boxes slightly, right? So how are we going to do this? Well, let's say that we want to rotate this cube along the each cube should be rotated along the axis, around the axis by a given degree. So and this degree will be defined by the proximity of those boxes to this line. So let's say if this box is very close to the line, it will be rotated more. If this box is far from the line, it will be from the curve, it will be rotated less. But they are deformed, so we cannot rotate them here. We need to rotate them somewhere else, right? It looks like something impossible and maybe not very intuitive, but this is where the data management can help us a lot, because what does each of these cells do with proximity to this curve? Basically, each of these cells has a center, right? And each of those centers is at a certain distance from this curve. Yeah. So you can just, first of all, we can take this curve, we can bring it to Grasshopper. And now we're just going to use the pull point to evaluate the distance from this curve to each of those centers, right? Okay, so now we have the distances for each of those cells. We're going to use the list normalizer component. It comes from the Heteroptera plugin, which is a super useful one. It can be downloaded from Food for Rhino. It's an open source, like free. No, sorry, not open source, but it's free. It's a free plugin, so you can use it. And you see it normalizes the data as a tree. So it takes the bounds of the entire tree and it normalizes them all against the same domain. Now we're going to use the graph mapper, just in case. Again, we might not even need it. We might need it for some design features, but it's not obligatory, let's say, to use it here, because it will work even without it. So let's construct a domain, and let's say that we're going to rotate our shape from 0 degree to 45 degrees. Yeah, something like this. Yeah, so for each of those cubes, we actually have a single value for rotation. But we cannot, as we discussed, we cannot rotate those cubes here because they all are different, they all are deformed. But how about we take each of those cells and we place them here? Like, we don't do it physically, but we imagine that for each of those cells we have a twin which is not deformed and which stands in this point. So there is nothing which prevents us from having, let's say, how many twisted boxes do we have? We have 209 twisted boxes. So we can easily have 209 boxes here, which are not twisted, which are not deformed, right? And we can make a rotation for each of those boxes here, and then we will take it back and we will bring it to its place in this wall, because we have all the cells from here, every cell here has a twin here, right? An undeformed twin, which can be rotated, manipulated, and then can be placed back into its twisted position. Yeah. I hope it makes sense. You will see what I mean in a few minutes when we finish this exercise. So yeah, let's take it from here, and let's place it into the boxes. Yeah, okay, whatever. We have these points, we have these distances, and now we just need to create as many of these boxes as we have it here, right? So, okay, first of all, I'm gonna create the axis against which we'll rotate this box. So I'm gonna start from here. Yeah. I'm gonna take this box. The axis, I'm gonna just use a x, y, z vector, and each of these parameters is gonna be set to 1, which will give us an axis which goes at 45 degrees to our box in all planes. So let's say rotate 3D. This is our axis. This is our geometry, yeah. And our center is this point. We have this center. And the angle is going to be provided from here, yeah. Also be careful to right click and set it to degrees, because by default Grasshopper works with radians. And it's convenient for mathematicians, but it's not convenient for us. I mean, for architects, for designers, it's not very, and like normal humans, it's also not very easy to work with these values. So let's just convert it to degrees. Yeah, you see, these are all the twins, non-deformed twins of those cells, right? So we have 209 boxes here. So what we will do now, we will just take those boxes, we place them here. Yeah, you see. And we also need to make sure that here we're gonna have as many as we can actually graft it. Yeah, we'll graft it. And we will use the tree statistics to make sure that we have as many outer boxes as the inner boxes. Yeah, so we're gonna duplicate data. Yeah, as many times as the number of tree branches we have here. Yeah, so if we have 209 twisted boxes, it means that we need to duplicate our large boxes 209 times. So, sorry, not here, but here. Yeah. And then I'm going to graft it. There we go. You see? Actually, there is no need to graft it. It's been already grafted, but whatever. Also, let's be careful. Let's make sure. You see that here we have a clear data mismatch because the tree branches have different lengths. So what is important for us here is to make sure that this data structure is going to be principal. So first of all, we say right click and say it's principal, yeah. And now we start having our data structure in order. So we basically need to make sure that the data structure here is the same as data structure here, right? We have the same paths here as here, which happens now, so it's good. And yeah, after that we're just gonna place them into the corresponding boxes. So as you can see, if we go to front, you see that those elements, they almost do not rotate, and those elements, they rotate the most. We can also do the opposite. We can change this domain to this, you see. And now if I increase this number, you see how our entire wall basically starts moving. And if we also spice it up a bit more, we can make it more contrasting, right? So that there will be the gradient between the rotated and not rotated boxes will be sharper, like it will almost not exist here anymore, right? This is what I personally find really useful for all the operations when you're dealing with some complex facades or complex geometries in general. that you can by using a correct data structure, you're able to deform the geometry when it's light and simple and it stands on the ground. Let's say it's super like simple. You change it and then you place each of them. You place into a separate cell in your deformed grid. So, or not deformed, not necessarily deformed. You can also have them all like the same, let's say straight, but if you have a complex shape and you need to place the objects along it, it also helps to like form them in one place and then use some components to put them in their position, right? It's easier. It's always easier in Grasshopper if you start from making one element, right, and then you place it in, let's say, 400 positions. Then if you start creating those elements already in their positions. I mean, it might make sense sometimes, but if you can avoid this, it's better to use this technique rather than forming them in place. Yeah, so you just make it in zero position and then you place it in their real position, right? Okay, so and now I'm going to show you a slightly different approach, which I promised to you, which is yeah, it's about the points that I showed you before. I'm gonna hide this thing. Actually, I'm gonna copy it because we will need it later on. But yeah, first of all, I'm going to check those elements. Okay, fine, they're here. Yeah, this approach is slightly different, but basically it's also quite it's a bit similar, let's say. But this time we need to have non-deformed boxes inside the deformed twisted boxes. So the twisted box itself will be deformed, but the cube in the center will have to stay still. It will have to be just rotated but not deformed. So this is quite important. So what I'm gonna do now, I'm gonna use the same graph mapper, right? I'm just gonna take it's just the script is going to be different from here onwards, right? But not too different from not different up until this part. So what we need to do now, we need to take those points, right? Like these points. Actually, yeah, only those points, only the points from the larger box. Yeah. And we need to place them inside those boxes. So I'm gonna take yeah, I'm gonna take the point container, connect it to the vertices. I'm gonna bring it into the box morph, and I'm gonna preview on. Yeah, so we have these points in the, let's say, strategic positions, right? And now what is important is to place those rotated boxes, like from here. It's important to take them and place them into those boxes without any deformation. So how can we do this? Well, we're just going to take those centers from here. Again, we use another point container to contain those centers. And I'm going to use the move to point component, super simple one. I'm going to take those rotated parts. I'm going to take those centers. Yeah, this one center, because it's common for all of them, they all share it. I'm going to place it here. You see? 1 second. So we have, yeah, we need to draft those points. It's very important to make sure that all of those cubes are rotated correctly. You see? The problem with this method, though, is that the dimensions of those boxes are gonna be are not gonna be the same as the dimensions in a method before, right? So for that method, it can be solved pretty easily. We just need to make sure that the dimensions of this box, sorry, this box, they're kind of corresponding to the dimensions of those boxes. It's not possible to make them exactly the same, but it's always possible to let's say take one of those again, it's going to be in a very approximate sorry, flatness. not reverse, flatten. It's going to be a very approximate sorry, my English is failing me. It's going to be a very approximate measure, but still, it's better than having it like it is now. So I'm going to take this box and I'm going to create a bounding box from it. After that, I'm going to deconstruct this box, and I'm going to take the approximate average dimension of this box. Let's imagine this cube. It's a cube. It's not a cube, clearly, right? But let's imagine how big would it be if it was a cube. And for that, we're going to take x, y, and z. We're going to deconstruct domain. Here we can connect them all to the same input, right? We get 3 numbers in each of the outputs, and then we just need to subtract the start from end, and these are going to be our dimensions, and then we just need to find the average one. Yeah, so this is it, and we're going to use this number as the parameter here, right? So you see that now these boxes are, first of all, they're much smaller. Second, they are really close to those. Well, actually, they're still pretty big, but they're already better than what we had before. We can also, if we don't like their size, we can also change, because that box was disproportionately long, so it's clearly not an average box in our yeah, actually it's funny. If we want to go even further, we can just flatten our tree here, and we can find the volume. Sorry, we need to find a bounding box, of course, because the twisted box doesn't have any volumes, right? So we need to find the volume of the bounding boxes. Yeah, so we take it like that. And find an average one. I mean, this is really probably even irrelevant, and it's quite complicated, but yeah, we can say inequality, intolerance. It's another really useful component from Pufferfish plugin. So we're going to use it to take one of the average boxes, let's say. I'm going to set the, because you see the value is really high, so I'm going to set the tolerance to another high value. I'm going to say cool pattern. Here I'm going to select the, yeah, you see we have 2 twisted boxes which kind of follow this requirement. Yeah, I'm gonna take only one of them here. I'm actually gonna create a cluster from this, so that we don't have to waste our precious space in Grasshopper, just for the sake of navigation. I'm gonna do it. Yeah, so let's keep it here, and yeah, now I'm more or less happy with the quality of those boxes. Alright, so now we just need to repeat the same operation. We just need to take the edges, just need to deconstruct brep, and we need to connect the points right here and here. So no, sorry, not here, but here, right? This one. Is it correct? Yeah, I think so. Yeah, and then we just need to take the brep edges from these breps. Just need to take the edges and the points. There we go. Yeah, here it clearly twisted a little bit, which is kind of annoying when you deal with twisted boxes. So what I'm gonna do, I'm gonna try to how can we solve it? Let's see. Not sure if the closest point will work here, but we can try. Say this point, we'll try to get the closest point from this set. 8 points here, 8 points here, let's try. No, it's really worse. No, forget it. Let's keep it like this. There are some manipulations for twisted boxes which can be taken here, like reordering the twisted boxes orientation and other things, but I'm not sure, to be honest, how yeah, it will take a lot of time. And actually, yeah, if you want to, I think it's another topic which should be covered in a separate session. So if you're interested, please let me know. I'm gonna make a separate session about twisted boxes in general. But yeah, a simple method to resolve this thing can be trying to rotate those boxes yeah, against these points by, let's say, by 90 degrees. I'm gonna create a slider with degrees 90 and multiply it by some numbers. Let's see, 2. Let's try. Is it better? No, not really. 1. Nope. This one looks good actually to me. This one is fine. Yeah, let's keep it like that. Okay, so yeah, I'm gonna put scripts in something that looks like order. Let's see. Let's take it like this. Like that. Okay, so we have two sets of curves. Yeah, this one and the other one. So one of them is very is deformed, but this is probably the most a more coherent one because all the boxes are kind of yeah, they are kind of, there are no intersections of lines with lines and some weird angles. So let's go with this one actually, and then the other one you can either do it, you can either try resolving it yourself, or you can yeah, drop a comment and I will maybe do another another stream, as I said, about the twisted boxes. So we will cover this topic a bit more in detail. Because right now I wanted to show you how to convert this all into a lattice structure. And I guess most of you are already familiar with such a tool as the multi-pipe. So I think from now onwards it's quite straightforward what we're going to do. We're going to flatten it. We're going to use discontinuity to find the points. Again, we're going to flatten the points. It's better to almost never flatten anything in your Grasshopper scripts, but right now, for the sake of time and like simplicity, we're just going to do it because we're dealing with only one wall. So if we dealt with multiple walls, we will have to use shift paths instead to make sure that we're going to deal with each wall, not all of them all together, right? Because it's going to be it's going to mess up our workflow. But now we can afford this, we can do it. So let's flatten the tree, and yeah, let's go to yeah, let's just type multi-pipe. So we're gonna use those curves. Yeah, let's try. Actually, we need to take the size points and the node size. So again, I suggest us to just grab this part of our script with this curve and with the scroll point component, and connect those points here. let's say maybe 45 is too much for the node. Let's keep it at 5, let's say. Yeah, we can edit the slider to the maximum of 10, and we can add some decimals. Maybe 1 decimal should be fine. Yeah. And here, of course, we cannot keep it at 0. We need to have it at least at 0.5 maybe. And yeah, let's disable this component for now. Let's make sure that our data is in order. So we have these curves, node size here, and size points here. Yeah, looks fine to me. I think it's kind of, yeah, looks like it's kind of in order. Right, so let's have a look. I think it might take a lot of time, so let's be patient. Yeah, in the meantime, again, just a reminder, please let me know if you have any questions, and also, that's actually was fast. Also, if you would like us to cover something specific in our next live sessions, and also, yeah, if you would like to apply for an individual course or for a group course, also drop us a message on Instagram or like anything. We will be more than happy to help. Yeah, basically that's it. Okay, so yeah, you see the lattice is looks quite good to me. I'm just gonna change the values so that it gets thinner towards the curve and thicker towards the sides. And then I'm going to use the custom preview to make sure I see the geometry and see clearly. So let's hide this. Let's change the color to something fancy. Yeah, that's it. Looks good to me. Let's enable the solver again, and let's actually look at it in rendered mode. I think it's gonna look quite good. Again, I don't know. Yeah, you can see that I'm actually quite happy with the result, how it looks. Yeah, you see that basically we create this heterogeneous structure. It's not very fast. It takes 11 seconds to complete, which is, to be honest, it's not too bad. Yeah. And yeah, we can play with the values. We can play with the graph. We can also change those numbers. But of course, I think for the sake of time, it's better to disable the solver, because to disable the solver, yeah, like you click the central mouse button and you left click on disable solver, and then you can change whatever you want, and after that you go to the multipipe again. I'm gonna disable it. I'm just gonna show you one cool graph, which is called sun summation. I personally really like it because it allows you to get relatively complex structures without much effort, which is always good at the design stage, at the early design stage, when you need to have a good result, or like, let's say, attractive result relatively fast. But of course, later on at optimization stages or at execution stages, you will need to yeah, you need to design it more carefully and more properly. All right, so yeah, that's what I'm talking about. See, we start getting this kind of interesting pattern of thicknesses, and I personally find it quite attractive. So, also, by the way, speaking of our Instagram, if you have any nice results after any of our sessions, or if you would like to get featured, if you're a designer, an architect, a graphic artist, drop us a message, drop us your images, and we'll be more than happy to share them and to tag you. So yeah, we'll be happy to see your results after after our tutorials. Alright guys, thanks everyone for the attention and for attending the session today. We're always open to collaborations and discussions, and we'll be happy to answer your comments. So please let us know what you would like to see next. I hope it was useful. And yeah, wish everyone a nice coming week. And thank you very much. That's